Okay, everyone. So, if you recall from last time, we were talking about how we can choose a equilibrium from multiple equilibria. Okay, so one way to do so is to choose the one that gives the largest total payoff. So what I mean by total payoff means we're talking about so far we are only talking about two-player game, right? There's only two players. But there could be more than two players. For example, you can consider a prisoner's dilemma where there are three people. Okay, that's possible. Okay, I'm not gonna go into detail, but the point is, what I mean by total payoff would be the sum of payoff from everyone. So in a two-people game, two-person game, then that would be simply the payoff sum of the two. Okay, the idea here is that among different equilibria, we would like the result to be the one that has the highest total payoff. Okay, that would be optimal or preferred. Okay, and another way to think of this is to select the symmetric equilibrium. Okay, for example, the reason why we want a symmetric is to consider sometimes the equilibrium are asymmetric. Wait, do people understand what I mean by symmetric and asymmetrics here? No? Okay, so symmetric means both players choose the same strategy. Okay, and asymmetric means they choose different strategy, basically. So this is a case where both players have the same strategy space. Then we can talk about symmetric and asymmetric. So for example, we can play a game where the player A chooses from left and right, and player B chooses from up and down. Okay, then there's no definition of symmetric because they are just having different action space. Okay, there's action that they can choose are just different set. So there's not a way of defining symmetric. Okay. And in BOS, there's sorry, I forgot to mention that there's still another way to define symmetric. That's when the payoff are symmetric. So when both players are getting the same payoff, we also call that symmetric equilibrium. Okay, that's another way to define it. So here, the textbook defines the second way. So it says that in the BOS, either of the pure equilibria would satisfy the first criteria. Remember, the BOS, they choose to go to ballet or boxing. So the pure equilibria would satisfy the first criteria, meaning they both go to ballet or both go to boxing. Those two satisfy the first criteria. They both give the same payoff. But the mixed equilibrium will satisfy the second. Because in the mixed equilibrium, they both get the same payoff. Okay. And the third way of doing so is select the so-called focal point. So focal point, you can define it this. You can think of it as this way. So suppose you and your best friend is gonna meet at a train station, but you forgot to bring your cell phone. Okay, which in modern day that means you have no way to connect your friend. Okay, and your friend also don't have a way to connect to contact you. So but this train station has more than one meeting point. So you know one of the meeting point will be the destination, but you don't know which. And you only care about meeting your friend. So if you meet your friend, that's a positive payoff. Say the payoff is 1. So if you meet each other, both of you get a payoff of 1. Okay? But if you don't meet each other, both of you get 0. This is called a coordination game. Okay, you want to coordinate on one of the meeting point. And so in this case, you don't there are multiple equilibria. Okay, in this case, every meeting point you meet at everybody choose the same meeting point are equilibria, and also randomly choose one of the meeting point, and the other person also randomly choose one of the meeting point is also equilibria. Okay, but it's really hard to decide which one is the best in that case. There's no focal point. Okay, but suppose you somehow know that all the meeting points are sort of similar to each other, but there's one meeting point that you both have a memory. Okay, you guys have a shared memory at that meeting point. That means, translating to math, that means when you guys meet at that specific meeting point, the payoff is not 1, but maybe 1.1. There's a 10% increase in your payoff. In this case, a lot of people would just simply choose that meeting point because it's focal. Okay? This is an example easier to understand. The counterpart of this example is, suppose there's a meeting point, you have a really bad memory, you have a shared bad memory, or that place is specific or especially shady among all the meeting points in that train station. So that means when you guys meet there, instead of getting a payoff of 1, if you guys meet there, you get a payoff of maybe 0.9 or 0.8. It's actually lower than all the other meeting points. But there are still maybe 5 more meeting points that all gives you a payoff of 1, conditional on you actually meet there. But you don't know which one to go, right? But if there's one that gives you even a slightly lower payoff, with a very high chance you will end up meeting at that point, because that's also focal. Yes?
Is it focal because it's different for the fibers?
Yeah, it's more salient or more focal, that's what it means. It just looks different. Yeah, so you want to choose the one. So the reason why I gave 2 examples, one has higher payoff, everyone could understand that, right? But even with the lower payoff, it still is different. So it's still, and you should know that if it is a minus payoff, nobody would meet me there, because even if I don't meet you, I still get a 0 payoff, and that's still better than negative payoff, right? But it still has to be a positive one in this example, but you get the point. Okay. Yeah, so I already gave the example here. So the textbook already gave another example for come back for alumni weekend, but the idea is the same. Okay. So now we move to sequential game. Okay. So what is sequential game? Basically, people plays by taking turns. That means sequential. Okay. So the example here is still battle of sex games, but here we assume that the wife chooses first. Okay, just like in many families, wife is actually the master. Okay, so the wife chooses first, and now the husband actually have 4 strategies instead of 2. Okay, this is where strategy and the action differ, which is really important. Okay, the reason why husband still have only 2 actions. His action is go to ballet or go to boxing. That's his action. But his strategy is more complicated because he can observe his wife's choice first. So the ballet written here and boxing written here are the wife's choice. Okay, so the first strategy that this husband can do is, if the wife go to ballet, I will go to ballet. If the wife go to boxing, I will go to ballet. That's one strategy. Okay, you might want to argue with me saying that, he's not going to do that, because if I observe my wife go to ballet, I will go to ballet, but if I observe my wife go to boxing, I should also go to boxing, right? But that's not the point here. When we're talking about action and strategy, we're not talking about what will happen. We're just talking about what is possible. Okay, so this is one possible strategy. And the second possible strategy is that if the wife go to ballet, I go to ballet. If the wife go to boxing, I go to boxing. The third one is, if she goes to ballet, I go to boxing. If she goes to boxing, I go to ballet. And the last one is, if she goes to ballet, I go to boxing. But if she goes to boxing, I also go to boxing. So that's why there's 2 by 2. There are totally 4 strategies. Not 2. So this kind of strategy are also called contingent strategy, because it's contingent on your opponent's choice. Okay. So notice that the wife still have only 2 strategies, because the wife moves first. So she can still only choose from her 2 actions, ballet or boxing. There's no way she can choose something contingent on her husband. Okay? Is that clear? Yes.
Can you repeat this for the contingent strategies for
Repeat the part for contingent strategy.
where does it have for
Do you understand the 4 strategies here?
no?
Okay, so this line means if the wife go to, so first of all, you understand that the ballet and boxing that I circled here are wife's choice. You understand that, okay? So this is conditional. Okay, so conditional on my wife go to ballet, I will go to ballet. Conditional on my wife go to boxing, I will go to ballet. Do you understand that? That's one possible thing I can do. So that's called strategy. Is that clear? Okay, and this is just one possibility, right? So that's why I can write 4 possibilities. Do you understand how I write these 4? Right? Okay. So that is what I mean by contingent strategy. So the second mover can observe what the first mover did, and then choose a corresponding action. Right? And this whole package is called strategies. Okay. And so if we write this sequential version of the battle of sexes into a normal form, notice that now the husband has 4 strategies, as I told you, but the wife still have only 2 strategies. So the normal form, the same game, just I move from simultaneous game to a sequential version. Now it's a 2 by 4 game matrix, not a 2 by 2 game matrix anymore. Okay? But no matter how many grids I have, the way to check for Nash equilibrium is the same. Okay? What I mean by that is, for example, let us check whether this is a Nash equilibrium. So actually I should write this, sorry. So whether the husband choosing ballet, boxing ballet, and the wife choosing ballet, whether this together ending up at this grid, is that a Nash equilibrium? How do you check this? You check whether wife or husband has an incentive to deviate, right? Okay, so in this case, would the husband has incentive to deviate? No, because this is his payoff. This is the highest payoff he can get. Conditional on his wife go to ballet. So 1, 1, 0, 0. 1 is already the biggest. So he cannot move to a better place. Also, the wife cannot do something better because wife is already getting the highest possible payoff in this game. That's 2. Okay, so moving to boxing only gives her 0. Right? I want to do this one is because I want to make sure you guys still remember how to check for natural equilibrium from last week. Are we good? Are you good? No? Okay. What's the definition of natural equilibrium, Ben?
Both parties have an outcome or result.
No. The definition is there's 2 ways to define this. Either what I just said about 2 minutes ago, that both party doesn't have an incentive to deviate from the current strategy. The second one is they are both using the best response. You can check just from the slide, like few slides before. Okay, it's the same week. Okay, let me just go there. Make sure people. So when we were talking about equilibrium, we first define what is best response. Okay. A strategy that produces the highest payoff among all possible strategies for a player given what the other player is doing. Remember that? Okay. And then we define the Nash equilibrium as a set of strategy, one for each player, that are best responses against one another or against each other. So when they are both using a best response against the other one's strategy, so that what it means by the first player used strategy 1, the second player used strategy 2, and somehow strategy 1 is a best response to strategy 2, and strategy 2 is a best response to strategy 1. That's the definition of natural equilibrium. Okay? And because of this definition, we have a way of solving it using this line. If we both play our best response strategy, then neither of us has an incentive to deviate. Okay. This idea of equilibrium is taken from physics, sort of. What it means by equilibrium in physics is usually what something in an equilibrium state is something that will not move. Right? So the idea here, the thing that's moving here, that's possibly moving here is the strategy. I can choose a different strategy. What it mean, when I choose a different strategy, that means I deviate. That's what a deviate means. Okay? So because I'm already used the best response to your strategy, your current strategy, you are also using a best response to my current strategy. So there's no way that either of us has an incentive to deviate. Okay? And based on that, we talk about 2 ways to solve the game, or 2 ways to find the natural equilibrium. One is called inspection, which is the one that I just used. The other is the underlying method, Okay, so go back to our current situation, current slide. So I will do the inspection again. Okay, so I will do another one maybe. This one, is it in natural equilibrium? How do I check that? I first check whether husband has an incentive to deviate. The husband is currently getting a 1. Can he do better by getting something more than 1? If he chooses this one, he still get 1. If he chooses this one, he still got 0. If he chooses this one, he still got 0. So indeed, 1 is the best he can get now. Okay, so husband has no incentive to deviate. And does the wife has incentive to deviate? The wife is currently getting a 2. But if she moves to boxing, she will get 1, which is lower. So she also doesn't have incentive to deviate. Since neither of the party has incentive to deviate, this is a natural equilibrium. So both these two are natural equilibrium. Yeah.
Is the third one natural equilibrium?
This one?
Yeah.
This one is currently obviously not. Because currently the husband is getting 0. If the husband moves to either of these two, then he will get 1. 1 is greater than 0. Okay? The other one, the underline method goes like this. So I underline the best strategy, best possible, best response, basically. So given that the wife is going to ballet, what is the husband's best response? Husband's best response is choosing this strategy or this strategy. So I underline the payoff here. Do people get that? Okay. If your wife chooses boxing, then this strategy and this strategy is the best response. So I underline the 2 here. Now I go to the husband. If the husband chooses this strategy, the wife's best response is ballet, right? So I underline the 2 here. If the husband chooses this strategy, this one, okay, this line, okay, then wife's best response is still ballet. So I underline the 2 here. If the husband chooses this one, then choosing ballet or boxing both give her 0. So both are best response. So I will underline both the 2 here, the 2 0 here. If the husband chooses this one, then go to boxing is the best strategy. So I will underline the 1 here. And remember that as long as both the payoff has a underline, that means where the best response meet each other. So this one, and this one, these 3 are natural equilibrium. Are we clear?
Does it make sense to do that if the wife chooses first? Like you said, when dealing with the husband's strategist, you said if the husband chooses this, the wife's best strategy is to choose.
That's the definition of how do you find best response.
Yeah, but does it make sense if in the game the wife chooses first?
Doesn't matter. Yeah. You are talking about what we're going to talk about next once, what makes sense. But we're not talking about what makes sense here. It's just a mathematical definition. That's how you find the best response. You need to really understand, among all these kind of mathematical questions or game theory or decision-making problem, the first thing that you should really learn is the definition. and you follow the definition, and you get to something. That's the key that you should learn. So that's why the first thing is you need to learn how to check for natural equilibria. Okay, so that's how you find natural equilibria. But the second question, actually, Jeffrey already mentioned, is whether this makes sense. How do we define what makes sense? What makes sense? Okay, we were used a word called credible threat. Okay, so here, for example, this one. Wait, is that one? Not that one. This one is more obvious. The other one as well, but I will talk about that one later. This one is clearly a threat. Translate into English. This one is that the husband is using this strategy. What is this strategy? Can someone translate that into English to me? Come on. Anyone? Yes, no matter what the wife does, I will always choose boxing. Do people understand why I say this is clearly a threat? No? This is like your girlfriend or your boyfriend is telling you that he or she wants to do something that you just don't want to do, and you actually and then you threaten her or him that I will just, no matter what you do, I will just play my video game at home. Or in this specific example, so clearly if you go to boxing, I want to go to boxing with you. But even if you go to ballet, I actually want to go there with you, but I threaten you that I will actually go to boxing instead. No matter what, I will just do boxing. So I force you to choose boxing as well. That's why it's called threat. Is that clear? Okay. So this threat is non-credible. The reason why it is non-credible is because if the wife actually chooses ballet, first, then the husband's best response is to choose ballet, right? Right? Okay. Similarly here, this strategy is no matter what the wife does, I will go to ballet. And this part is non-credible. If the wife go to boxing, I actually will also go to boxing. I will not go to ballet. So this claim is non-credible. You cannot convince your partner that. So this story goes like this. I know, like Jeffrey said, the wife is choosing it first, thinking of you as the husband, okay? And you're telling your wife that although you move first, but no matter what you do, I'm just gonna do this. I'm just gonna go to ballet. I'm just gonna go to boxing. Either way, that doesn't make sense. It's non-credible. You cannot convince your partner. Right? So that's why these two are non-credible threats. Just the word threats here is just a general terminology. Okay. The reason why the way we define this will be clear in the next slide. So the only credible one and the prediction of our model is that wife will choose ballet first, and the husband's strategy is if the wife goes to ballet, I will do ballet. If the wife goes to boxing, I will do boxing. Okay? And how do we make it easier to find this solution? We will use something. We will actually say that whichever satisfy this credible threat criteria, we delete these two, right? We delete these two. And the one that survive, we say that this is not just a Nash equilibrium, A Nash equilibrium, but it is also a subgame perfect equilibrium. So clearly, subgame perfect equilibrium is a subset of Nash equilibrium. Nash equilibrium is a bigger set. So every Nash equilibrium, every subgame perfect equilibrium is a Nash equilibrium, but not the other way around. Okay? Okay, so how do we actually find this SPE? We use something called a backward induction. Okay, it goes like this. So instead of, I know the wife chooses first, but I don't do the game this direction. I do it backward. So I do it this direction. Okay? So I ask the question, so following question. So in this subgame, this proper subgame, okay, we define, let's first define subgame. Okay. This whole thing is a game. What is a subgame is just a part of this big game. And what is proper subgame is part of the game tree starting with a single node, including everything branching out below it. So this one is a proper subgame because it's starting with a node here, right? It's a node here. And it includes all the branching out, right? And here, this is also a proper subgame because it includes all the branching out. This is not a proper subgame. This is a subgame, but not proper. Because it's starting with a node, but it doesn't include this line, this one. Understand what I'm saying? So it has to include everything that starting from that node. Okay? We still have the third proper subgame here, which is everything. Because it also started with a node and it includes obviously everything. So the whole game is also a proper subgame. Here we have three proper subgames. Oh, sorry. And the definition of SPE is that basically the strategy needs to be a Nash equilibrium in every proper subgame. Okay. The reason why these two that I cross out does not satisfy the subgame perfect equilibrium because in some subgame it is not a Nash equilibrium. It's not the best response basically. So how do I actually find this? So like I said, you need to do a backward induction. And what I do is consider when the husband is standing here, what would he do? He will always choose this one because it gives a higher payoff, right? Because 1 is greater than 0. 1 is greater than 0. Is that clear? Okay. How about here? If the husband is here, what will he do? He will choose here, right? Because 2 is greater than 0. And now the wife is considering what to do. Wife knows that if he chooses ballet, husband will go this way. If she chooses boxing, husband will go this way. So she's choosing between 2 and 1, which one is bigger? 2. So she chooses this way. Okay? So this is how you find, so now you understand, now you basically find this one. So how do I write this SPE? The SPE, you need to write this, okay. Something like this. The formal way is this, ballet, and then conditional on ballet, I will go to ballet. Conditional on boxing, I will go to boxing. So this is the wife strategy. This is the husband strategy. And you use a parenthesis to group them together. Okay, but it is okay for you to write something like this. I will understand what you're writing. Okay? But it is not okay for you to write this. You might want to say, okay, so the result is that they both choose ballet, right? But that's not the definition of equilibrium. Remember, our definition of equilibrium is that it's a strategy profile. It's a combination of strategies, right? The first person needs to choose a strategy. The second person also has to choose a strategy. But here, ballet is only an action to the husband. Not a strategy. Okay? This is also very important. I want you to at least so walking out of the game theory short course, you should at least be able to explain to other people what is Nash equilibrium, what is subgame perfect equilibrium. These are the only two that I will definitely test in the midterm for one thing. For the second thing, I would highly recommend that you understand. Okay. I know a lot of people, when talking about game theory, what comes to their mind at first is the prisoner's dilemma. But that's not that important. The most important thing is equilibrium, the idea of equilibrium. So you should understand what is Nash equilibrium, what is SPE. That's most important. Okay? Questions? No? Okay. Now, there's a special class of game called repeated game. But repeated game, if it only plays with a finite, definite or finite time horizon, that means it only plays for finitely many times. For example, if there are two players, player A and player B, they first play the prisoner's dilemma for once, just like what we learned before, and then they play another prisoner's dilemma, the same game, but they play it again, and their payoff is simply the sum of the two periods payoff, without considering the time discount. But we will consider the time discount later. So we're just repeatedly playing the game and get all the payoff from each period. Is that clear? Okay. And since this is actually has stage, it's a sequential game now, right? Prisoner's Dilemma itself is a simultaneous game. But if they play twice, then it becomes a sequential game. Because in the second round, when we play the second prisoner's dilemma, you will be able to observe what the other person did in the previous try. And your strategy can conditional on that. So if you betray me in the last round, I will also betray you in this round. That's one possible strategy. Is that clear? Okay. Now consider we repeated the PD for 10 times. Because we're talking about sequential game, when we're talking about sequential game, we always want to find SPE, non-natural equilibrium. Okay, because there are many natural equilibrium that could exist but non-credible. Okay, so we only find the subgame perfect equilibrium. So, and can someone tell me, I just told you guys in the previous slide, when we are talking about a sequential game, how do we find the SPE? We use what? In a sequential game, how do we find SPE? What's the routine that we use? Yeah, backward induction. Okay? So we use backward induction. Okay? So imagine that we have 10 PD. So we play one PD, then PD1 and PD2 and so on to PD10. How do we do the backward induction? Where should we start? The first prisoner's dilemma or the last prisoner's dilemma? The last. Yes, that's how we call backward, right? And in the last prisoner's dilemma, since it is the last, there's no next round, right? And no matter what the previous history said, in the last round, this is just like we are having the first, just like what we had before, when we have only one round of prisoner's dilemma. Because everything is sunk cost, right? In the last round, it's just like the first time we played the prisoner's dilemma. Our prediction would be both people will confess. Okay? And then if both people will confess in the last round, in round 10, the backward induction would then take you to round 9, right? And if you know this person is going to betray you, confess in the next round, what would you do in round 9? You also confess. And the other person thinks the same way, so you will also confess. And since this is what happened in round 9, if you go to round 8, it will be clear that round 9 and round 10 will be played that way, so you will also confess in round 8. And so on, you go back to round 1, you will also confess. So actually, if you play for finite time, the same logic always follows. Since it's finite, we can always find the last round. And the last round, both people will confess. Then the last -1 round, everybody will confess, and so on. So the strategy here, the SPE here is actually player 1 strategy is I will always confess, and this player B strategy is I will always confess. That's the strategy. That's the SPE. Okay? This, by the way, this always confess is different from writing confess and confess. Okay? They're just different. This is still one round. But this is talking about repeated gain. That's just different way of writing. Okay? So, but in real life, this kind of presents the amount. We do see people cooperate. We do see both people play silent. For example, I gave the OPEC example last time, right? The oil output blah 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 corporation. Sorry, I really don't know what it stands for, OPEC. But the point is, they actually sustain a relatively high oil price for a long time. Okay, it even caused a oil crisis in the 70s. Okay, so if you wait, how old are your parents? It's probably not old enough. Okay, maybe, I don't know. Yeah, but if your parents were alive in the 70s or 70 something, okay, 1970 something, very little. Okay, yeah, then probably not. But or your grandparents. Okay, your grandparents will definitely remember the oil prices. That's a global event. Okay, just like you will remember the COVID-19 this year, and you can tell your grandson about this. Yeah, and so back then the oil price was so high, basically. Okay, so that's why it's causing a crisis in the world. And my point is, they were able to sustain that high price. The prediction here is that we were never gonna sustain that kind of high price. Okay, you just translate the confess and silent into confess is equivalent to low price, and the silence equivalent to a high price, basically. Then, there's no way you can sustain. So the trick here is that since the definite time horizon one doesn't work, we can use an indefinite time horizon, or infinitely many rounds. One way to do this is actually consider that we play this game infinitely many rounds, and we discount the payoff. So suppose I'm getting payoff pi 1 in current period, and pi 2 at this is t1 or now. And this is t2, t3, and t infinity. Basically, I discount the payoff using the present value method. So pi 1 plus pi 2 divided by 1 plus r plus pi 3 divided by 1 plus r to the power of 2, and so on. Remember we did the present value in one of the previous chapter? I was talking about this. Okay? Another way to think of this infinity many round is the following. Let me finish this. Okay. I consider that after round 1, I have a probability of P going to the next round. So in T1, I will definitely play the game, so 100% chance. So let's use 0 to 1 probability. So probability of 1, I will play that game. But T2, I will only have probability P playing that game. And what's the probability that I will play the game in T3? Assuming the probability are independent. P to the power of 2, right? Because you have to first play round 2 and then go to round 3. So it's P to the power of 2. Is that okay? So T4 to the power of 3. Yeah. And so the payoff need to, so if I'm talking about expected payoff, I need to use the following formula. So 1 times, I will for sure getting pi 1, right? But I will only have a probability of p getting pi 2. And then probability p to the power of 2 getting pi 3. And so on. And you can observe that this one is equal to this one. If I let p equals to 1 plus r over 1, then these two will equal each other using this. So either you can think of as if they are actually playing the same game infinitely many rounds, or you can think of it as I play for this round, and then I have a probability of p playing the next round, and then probability of p playing the next round, so on. It's equivalent in a way. In the lab, when we run the experiment, you cannot tell your subject that you two will play infinitely many rounds for obvious reason, right? It takes forever. So you tell subject that your participant, your subject, that you only let them, you play for possibly infinity, many rounds, but each round will have a probability of p ending at that round. Okay? If we're good, then we will come back at 2 o'clock. 2 o'clock.